We need to verify that the circle given by x squared plus y squared minus 4x minus 6y minus 12 equals to 0. It's touched by the line 3x plus 4y plus 7 equals to 0. Let us begin. So here we have a circle which is centered at C, and it is touched by a line whose equation is given to us, let's say at the point A. Our goal will be to show that the line indeed touches the circle. So here what we'll do, we'll start with the given equation of the circle. We are given x squared plus y squared. So let's do one thing. We are going to rewrite this as x squared minus 4x added to y squared minus 6y equals to positive 12. The reason why I'm writing it as fashion, what we'll do, we'll try to make x squared minus 4x a perfect square, and similarly we'll also try to make y squared minus 6y a perfect square. To do that, what we'll do, we'll rewrite 4x as 2 times x times 2, and this number 2 is going to tell us that we are going to add 2 square to the first two terms and also subtract 2 squared from it, because this is a term which we are adding from our side, so we'll also have to subtract it to balance the equation. Then we come to the terms containing y, so we have y squared minus 6y. Now 6y can be expressed as 2 times y times 3. The number 3 is going to tell us that we have to add 3 squared and subtract 3 squared. Add and subtract that extra term. Fine, equals to 12. Now immediately, x squared minus 2x times 2 plus 2 squared, that's nothing but x minus 2 whole squared. So we've successfully converted it into a perfect square. Added to y squared minus 2y times 3 plus 3 squared. So that becomes y minus 3 whole squared. Now what we'll do, we'll transpose negative 2 squared, negative 3 squared and add it to 12 on the right hand side. That's going to give us the value. So we have 2 squared, that's 4. 4 added to 9, that's 13. So 13 plus 20 and 12, that's going to be 25, or simply 5 squared. Now if we compare it with the standard form of a circle, which is x minus h whole squared plus y minus k whole squared equals to 5 squared, then immediately we can find out the coordinates of the center, which is given by h comma k. So that comes out to be 2 comma 3. And the radius comes out to be 5 units. Fine. So we have the coordinates of the center of the circle. So that's 2 comma 3. Let's do one thing. Let's join point C and point A with the help of a straight line. So now we'll try to find out this length CA. So CA here is the distance of the point C from the straight line 3x plus 4y plus 7 equals to 0. So let's find out the perpendicular length CA. So this will be equals to, we'll take the absolute value, then we will take, now we have the equation of the circle, so that's 3x plus 4y plus 7 equals to 0. We use the perpendicular length formula. All we have to do is take the x coordinate of the center, so that's 2. That will get multiplied to the coefficient of x of the line, so that's 2 will be multiplied to 3. Added to the y coordinate of C, that's 3. 3 will get multiplied to the coefficient of y, so that's 4. To it, we are going to add the number 7, which is the constant term of the line, divided by the square root of, we'll have to take the square of the coefficient of x, so this will be 3 squared, added to coefficient of y squared, so that's 4 squared. So let's solve this. We're going to get 2 times 3, that's going to be 6. 3 times 4, that's 12, and then we have 7 added to it. So 12 plus 7 plus 6, that gives us 25. So this will be equals to 25 divided by square root of, so 3 squared plus 4 squared, that's going to be 25, which gives us the value 25 over 5, or simply put, this is going to be absolute value of 5. We'll consider the positive value since we are considering a distance. So we're getting the perpendicular length CA as 5 units. However, this CA is also the radius of the circle. So our radius of the circle, we also obtain its value as 5 units. So this is only true if the line touches the circle at point A. So we have verified that clearly this circle whose equation is given to us is being touched by the line 3x plus 4y plus 7 equals to 0 at the point A.